E2 reactions are stereospecific. So let's do an example. Phenyl ring, methyl, and a hydrogen. Remember, phenyl is simply an aromatic ring. That's all phenyl is. And let's put a bromine on here, and a hydrogen here, and how about another phenyl ring there? So a couple phenyl rings. Now we're going to treat this with a base. So it's going to be E2 reaction. E2 reaction. Now remember, in an E2 reaction, the proton being abstracted and the leaving group must be anticoplanar. Have to be. There's no other way to do it. So that means we have to rotate this thing, this carbon, to put the bromine where the phenyl ring is. Because I think everyone will agree that right now the hydrogen and this pH ring are anticoplanar. They're in the same plane. They're on the plane of the screen here. And they're anti. This one's up, this one's down. They're anti. So we need to rotate this thing to put the bromine down here. So let's do that. Let's just make it happen. Leave the left carbon alone. Put the phenyl ring here. Put the CH3 back here. I didn't change the left carbon at all. The left carbon stayed 100% the same. Now we have to be careful what we do here, because now we want the bromine to be here. So when we rotate this, the bromine came here, the phenyl ring goes up here, and the hydrogen comes out. Let's do that again. The bromine comes here, phenyl ring goes to the back, hydrogen comes to the front. Hydrogen to the front, phenyl ring to the back. That's how it works. So now, the hydrogen and the bromine are anticoplanar. So the E2 reaction can take place. Here's the base. Grabs that proton, cascades down, and the bromide leaves. That's how this reaction works. Now, the fact that it has to be anticoplanar dictates the stereochemistry. So now, you will see that the phenyl ring on the left carbon and the hydrogen on the right carbon are both facing towards us. They're both facing towards us. That means they're on the same side. So in the alkene that results from this reaction, I need to draw the phenyl ring on the left carbon and the hydrogen on the right carbon, both facing the same direction. Doesn't matter if it's up, doesn't matter if it's down, but they're facing the same direction. If you look at the methyl group here, it's got dashes, and so does the phenyl ring. So the methyl and the phenyl are both going away. So the methyl group and the phenyl group have to be in the same direction. And that's because of the stereochemistry of this alkyl halide dictates that when this bromine is anticoplanar, the phenyl has to be here and the hydrogen has to be here. Let's do the reaction again, but let's change the stereochemistry and see what happens. All I'm going to do is move this bromine to where the hydrogen is and this hydrogen to where the bromine is. That's all I'm going to do. Left carbon is exactly the same. All I'm going to do is put the hydrogen where the bromine is and the bromine where the hydrogen is. That's it. That's all I'm going to do. But remember, now we have to put the bromine down here where the phenyl ring is, right? So to do that, we have to rotate it this way. So the bromine is going to go where the phenyl is. The phenyl is going to go where the hydrogen was. And the hydrogen is going to go where the bromine was. Everyone's going to change positions. Okay? Let's do that. And as soon as I draw it, maybe you're already seeing it now, you're going to see the difference. So now, the bromine came here, so the hydrogen now is here, and the phenyl ring is here. So notice here, the phenols are on the same side. Here, the phenols are on opposite sides. Remember, phenyl, it's just an aromatic ring. pHs are on opposite sides. Here they're on the same side. So when we do the mechanism, you get something that looks like this, where the phenyl rings are on the same side of the molecule, and the methyl and the hydrogen are on the same side of the molecule. And that's what having a different enantiomer will do when you're doing an E2 reaction. You'll get different double bond stereochemistry depending on the absolute configuration or the stereochemistry of the alkyl halide. That's, I think, very interesting. Let's look at E2 reactions on cyclohexanes. This is where things, I think, get a little bit interesting. So here we have just a regular old bromocyclohexane. We're going to treat that with some base to give us the cyclohexene. Now, remember, the bromine and the hydrogen being extracted have to be anticoplanar. So anti is 180 degrees. At this point, there's nothing that's 180 from any of the hydrogens. The bromine is not 180 degrees from any hydrogen. So in this conformation, in this chair conformation, the E2 reaction will not occur because the bromine is not anticoplanar to any of these hydrogens. None of them are. None of them are 180. Will not occur. In order for the E2 reaction to occur, the bromine and the hydrogens must be 180. But we're in luck. We're in luck. We can do what's called a ring flip. When we do a ring flip, that puts the bromine in the axial down position. And now, if we look at it carefully, we can see that yes, indeed, there are protons that are anticoplanar to this bromine. This one and this one are anticoplanar to that bromine. That's a good thing. That means we can do the E2 elimination here. So the base cause that elimination to occur, and you form your cyclohexene like that. But here's the take-home message. In order to do an E2 reaction in a cyclohexene, the alkyl halide must be able to adopt the axial position. Up or down is irrelevant. The alkyl halide, the halide, must be able to adopt the axial position. If it can't for some reason, like the ring can't flip because there's a T-butyl on it, you cannot do an E2 because the bromine is not anticoplanar to any proton. Let's see an example of this. Now here is a very somewhat busy example. Don't let this phase you. Remember, deuterium is a heavy isotope of hydrogen. So deuterium and hydrogen, D and H, are essentially reactivity is essentially the same. So you can treat deuterium as you would treat hydrogen. So in other words, deuterium will behave like hydrogen in terms that deuterium can be acidic. So deuterium is abstractable in this reaction. So now, in order to see if this reaction will work or what the product will be, we have to draw this molecule in the chair conformation. So let's do that. And I'm going to say, let's call this carbon A, B, and C. So let's put bromine here. Let's call that carbon B. Carbon A will be back here, and carbon C will be up here in the front. So now the bromine and the hydrogen are on the same side. In other words, they're, if you want to say it, they're cis to each other. So here the hydrogen has to be up. So this hydrogen has to be up. The deuterium, however, is down. Deuterium is down. So let's go over here to carbon C. Carbon C, the hydrogen here has to be up, and the methyl group must be down. That's what it must look like, something like that. Okay? So now we can already see the deuterium is anticoplanar to the bromine. So this deuterium is anticoplanar to that bromine. So this is definitely going to work. The base will attack the deuterium. It'll cascade down like this. And you'll get, at the end of all this, you'll get that. Basically what happened was this, if you want to just draw the mechanism here, this deuterium did that. Now the only reason I know this works, is because I did this. If you don't do this first, you have no possible way of knowing that this will work. You have no possible way to do this first. All right, now let me show you the flip chair. Let me do the flip chair of this molecule here so you can see why the other ones don't work, why this one and this one are never abstracted. So I'm going to draw this as a flip chair. So now the hydrogen will be down, the bromine will be up, just like that. And in that case, this hydrogen will be up. The methyl will be down. Hydrogen will be up. Deuterium will be down. There we go, like that. So now you can see in the flip chair, the bromine is not axial. It's equatorial. These hydrogens are now axial. They can do reactions. The bromine can't. The bromine can't do an E2 reaction because it's not anticoplanar. It's not axial, so it's not anti to anything. So that's why this conformation will not give products. Now that conformation exists. That definitely is going to exist in that conformation. It's going to be an equilibrium between this conformation and this one. There's no question there. But this one will not lead to any product because the bromine is in the wrong orientation.